Hello and welcome to this video on identifying and using properties of the rank and nullity of a linear transformation. I had put up videos prior to this in which I found the rank and the range and rank of a linear transformation, and another video where I found the null space and nullity, or the kernel and nullity of a linear transformation. So this is kind of just piggybacking off of those. I'm hoping you're following along. I'm assuming you've watched something about the range and rank, null space and nullity before. So in this video I'm going to start off with a bunch of pages where I just redefine again for you the rank and nullity of a linear transformation, and talk about some properties that they have and how they're related together, and it'll all culminate with the Rank-Nullity Theorem of a linear transformation, which you will see is very similar to the Rank-Nullity Theorem for a matrix, right? And we're going to see that if you know the rank and nullity of the standard matrix associated with a linear transformation, well, then you know the rank and nullity of that transformation itself. Okay. So to start here, we're talking for the next few pages about the rank and nullity of a linear transformation. So this first page really has nothing to do with rank and nullity. It's going to lead up to it. So suppose T is a transformation between vector spaces V and W, domain and codomain. And suppose T is a linear transformation, right, meaning that it would satisfy the additivity and homogeneity properties that need to be satisfied, for a transformation to be considered linear. With the dimension of the domain, right, the dimension of V is, say, n, and the dimension of the codomain, right, the set W here, the vector space W, say that has dimension m. Well, if it's linear, remember every linear transformation can be expressed as a matrix transformation, whether it be with the vectors themselves or coordinate vectors with respect to some bases for the domain and codomain. So again, if T is linear, then T can be associated with a standard matrix, which I'll call A, of size m by n, right? And you'll see that too for any linear transformation. The standard matrix associated with it, its size will be the dimension of the codomain by the dimension of the domain. Alright, so the dimension of the codomain will be how many rows are in the standard matrix, and the dimension of the domain will be how many columns are in the standard matrix for a transformation. Such that for any vector in the domain, right, any vector v from v, if I apply this transformation to, again, when we deal with standard matrices, if the vector spaces are not Euclidean, meaning they're not R2, R3, R4, etc., then we're going to work with the coordinates of vectors relative to standard bases for these spaces. So T of transformation T applied to the coordinate vector for V with respect to, and I put this little EV down here, this is the standard basis for V, the standard basis for the domain. So if I take a vector from the domain and express it in terms of its coordinates with respect to the standard basis for the domain, I apply the transformation T to that, I should be able to express the output this way if it's linear, as a matrix, right, the standard matrix A multiplied by that same input coordinate vector. Right, and again, that EV is the standard basis of V, the standard basis of the domain, and this little bracket around V with the subscript of EV is the coordinate vector of V relative to EV. And again, I put up a video before on coordinates and coordinate vectors relative to certain bases. So if you'd like to go back and search for that or find that go ahead, right? You know, as a precursor to this, I'm assuming that knowledge of you. All right. Now here is a page. The next, I have a few points to make now about the rank. All right. Now, again, you've probably seen this word before, but here it is again. The rank of transformation T is the dimension of the range of T. Right, now remember, the range of a transformation was just all the outputs, right? All the vectors in W that actually get mapped to, or all the vectors in W in the codomain that have a non-empty pre-image, to use terminology from transformations. In other words, a little mathematical formula here, the rank of transformation T is equal to the dimension of the range of T. Well, we've also seen the word rank come up before in terms of, matrices, right? A matrix had a rank as well. The rank of a matrix A is the dimension of the column space or row space, right? Those were the same, those had the same dimensions, the column space and the row space, but we're going to strictly talk about the column space here. The rank of matrix A is the dimension of the column space of A. Now, if you remember, the column space of a matrix was the vector space spanned by all the column vectors of A, all the columns of A, basically every vector that can be written as a linear combination of the columns of A make up the column space of A. All right, so mathematically here, the rank of A equals the dimension of the column space of A. All right, col of A like that. All right, and the reason I bring both of these up is that they are actually going to be equivalent for a linear transformation. All right, so that's my third point here. For linear transformation T with standard matrix A, you'll see that we'll say that the rank of the transformation is exactly the same number as the rank of the matrix. And over here I've written kind of a recall, hopefully a refresher, going back to finding the rank of a matrix videos. Remember, the rank of a matrix is the number of pivot columns in an echelon form of that matrix. So if I do raw operations and put matrix A into either row echelon form or reduced row echelon form, the number of pivot columns that echelon form has is going to be the dimension of the column space of the matrix or the dimension of the range of the transformation. Either one, they'll be the same. All right. So this kind of gives me my what I'm going to be doing for this video. All right, I'm going to be finding a standard matrix corresponding to a given linear transformation, putting that standard matrix into an echelon form. More preferably, I prefer reduced row echelon form myself. And then just counting the number of pivot columns. Now remember, the pivots in an echelon form were those leading non-zero entries in each row with zeros below it, or in the case of reduced echelon form, with zeros below and above. And then one last little note about the rank of a transformation here. So again, for a linear transformation T, between vector spaces V and W, T is onto if and only if the rank of T equals the dimension of W, the dimension of the codomain. So remember, the word onto means that every vector, every element of W is mapped to. In other words, the range of T equals W, right, when it's onto. Well, if the range of T equals W, then that means they have to have the same dimension, right? So the rank of T, remember, that's the dimension of the range, and this is the dimension of the codomain. So the dimension of the range is going to be equal to the dimension of the codomain, if T is going to be onto. All right. So those are a few points to make about the rank of a transformation. On the next couple pages, I have very similar points to make about the nullity of a linear transformation. All right, so here we go. So remember that this is, again, hopefully all refreshers from previous videos if you've been watching. The nullity of a linear transformation T is the dimension of the null space, or the dimension of the kernel, right? I mentioned before in other videos that the null space of a transformation is sometimes referred to as the kernel of that transformation. So the nullity of a transformation is the dimension of the null space of that transformation. Now remember, the null space of a transformation was all the vectors from the domain that map to the zero vector in the codomain. Right, so that space of all the vectors from the domain that map to the zero vector under the transformation. And again, mathematically, I can write it this way. The nullity of transformation T equals the dimension of the null space of T. Right. And very similarly, right, this is very closely related to the null space of a matrix, right? And again, I'd put up a video before, a while back now, on finding the null space of a matrix. The nullity of a matrix A is the dimension of the null space of that matrix. Now remember, the null space of a matrix was the set of all vectors that, when multiplied by that matrix, give me the zero vector back as an output, right? So the null space of a matrix is again very closely related to the null space of the transformation. It's all the vectors that, when multiplied by A on the left side, you get the zero vector back. So that mathematically I write it this way: the nullity of a matrix A is equal to the dimension of the null space of that matrix. And these actually end up being the same thing in a linear transformation. Both of these nullities end up being the same number, which I've written here. So next point. For linear transformation T from V to W, vector space V to W, with standard matrix A, you'll see that the nullity of the transformation is the same number as the nullity of the standard matrix A. And again, a little refresher here as to how we can determine the nullity of a matrix pretty quickly. The nullity of a matrix is equal to the number of non-pivot columns in an echelon form of that matrix. So I'm going to take so this tells you how I'm going to work these examples I have later. I only have a couple examples later because I've done this before in other videos. I'm going to find the standard matrix for the given linear transformation, put it into an echelon form, again, whether it be row echelon form or reduced row echelon form, and then count the number of non-pivot columns, right? The number of columns that don't have a pivot in them, and that will be the nullity of the matrix, and also therefore the nullity of the transformation, the dimension of the null space. And then another point to make about the nullity of a transformation. Again, for a linear transformation T from vector space V to W, the transformation T will be 1-to-1 if and only if the nullity of the transformation is 0. So that means that the null space would be just the set with the 0 vector in it, right? And again, you've seen this in a previous video, hopefully, if you've been following. Remember, when the null space of a transformation was made up of only the 0 vector, right? Only the 0 vector maps to the 0 vector. Then the transformation will be 1-to-1. And what it meant to be 1-to-1 was that if you took any two different inputs, they will map to two different outputs. Right? You're never going to have two different inputs mapping to the same output in a one-to-one transformation. That will not happen. All right, so every pair of different inputs will map to different outputs in a one-to-one transformation. Okay. All right, so now after all those pages about what the rank is and some properties of the rank, what the nullity is and some properties of the nullity, we next have the statement of the Rank-Nullity Theorem, which you will again hopefully notice is very, very similar to the Rank-Nullity Theorem for a matrix. All right, so this is a nice relationship between the rank and nullity of a linear transformation. All right, so the Rank-Nullity Theorem for a linear transformation. So again, I'm starting the same way I did in the beginning of the video. Let T from V to W be a linear transformation, right, linear, with the dimension of the domain being n and the dimension of the codomain being m. And suppose this and it's linear, so it should have a standard matrix associated to it, and associated standard matrix A of size m by n. Then the following will hold true. Right. Again, this is for any linear transformation. The rank of the transformation, so the dimension of the range, plus the nullity of the transformation, right, the dimension of the null space, will be equal to the dimension of the domain. Right, V was the domain here. So I'll say that again. The rank of T, right, the dimension of the range, plus the nullity of T, the dimension of the null space, will be equal to the dimension of the domain. Okay. Now, like I said, this is very, very similar to the Rank-Nullity Theorem statement for a matrix. If you recall from my pages earlier, right, if the standard matrix for this transformation is called A, the rank of T is just the rank of A. The nullity of T is just the nullity of the matrix A. And remember, the dimension of the domain is I called n, and that's the number of columns of A. Right? So we have the rank of the standard matrix plus the nullity of the standard matrix equals the number of columns of the standard matrix. So just straight up the Rank-Nullity Theorem for a matrix. And again, I've written here the same thing I wrote on earlier pages. Just how do we find these things? The rank of T, the rank of A. Just count the number of pivot columns in an echelon form of the standard matrix. And how do you find the nullity of T, the nullity of A? Just count the number of non-pivot columns in an echelon form of the standard matrix. And the dimension of the domain, this n, should be the same as the number of, just simply the number of columns of the standard matrix. Wonderful. So lots of stuff there. All right, so I'm going to use this information, all this stuff I wrote in these pages, go over a couple examples. One, I'm going to have a transformation between Euclidean spaces, right, so I don't have to translate things into coordinates to find the standard matrix. And then two, a second example where I have a linear transformation between two non-Euclidean spaces. So in those cases, I will have to translate things, take vectors and change them to coordinates with respect to the standard bases for the domain and codomain in order to help me find the standard matrix. Once I've found the standard matrix, I'll put it into an echelon form and count the number of pivot columns, count the number of non-pivot columns, and be pretty much done, and talk about all the things we can say about that transformation. Alright, so the first example, and both of the examples I have the same instructions. It's just simply determine the rank and nullity of the given linear transformation. So I don't need to show that it's linear. Right? I am told that it's linear, so just believe it. You could, if you don't believe it, right, go through and show that that homogeneity and additivity property, those properties hold for this particular transformation. But again, I'm not going to do that because I am told it is linear. So we should be able to find a standard matrix, right? We should be able to express the output as a matrix times the input vector. All right, so here I have a linear transformation T, where my domain is R3, the codomain is R2. So inputs have 3 components, outputs have 2 components. So T of XYZ components here from R3 equals x plus 2y plus 3z for the first component, 3x minus 5y minus 2z for the second component. This is from R2. Alright, so like I said, we can if it's a transformation between Euclidean spaces, I don't need to change things into coordinates relative to some basis. I can just leave this the way it is and very easily write a standard matrix. Now remember, I mentioned before, the size of the standard matrix is going to be a 2 by 3. The dimension of the codomain by the dimension of the domain. So I'm going to have a 2 by 3 matrix here, 2 rows, 3 columns. For the I'm going to rewrite this output as a matrix multiplied by the input vector. Right, I should be able to do that if it's linear, and it is. So down the first column, just the coefficients of the first input variable x, so 1 and 3. Down the second column, the coefficients of the second input variable y, 2, then -5. And then down the third column, the coefficients of the third input variable z, 3, then -2. So there's the standard matrix, and then this is multiplied by the input vector x, y, z from R3 there. And just you can double check on your own that these are the same. If you multiplied this 2 by 3 times this 3 by 1, you should get this 2 by 1 back up here. Okay. Alright, so I have right here this 2 by 3 matrix with 1, 2, 3, 3, -5, -2. There is the standard matrix. And again, I'm going to call this, as I have on earlier pages, I'm going to call it matrix A. So, if all I'm asked is to determine the rank and the nullity, I'm not even asked to determine the range or the null space, which you could, right? But I'm not going to do that here. Right? I'm simply going to, through row operations, you can do it by hand, do the row operations by hand, or I'm just going to jump to a calculator. All right. Put this into an echelon form. Again, you know me, you've seen my videos hopefully. I prefer just popping things into reduced row echelon form, RREF. So I'll do that with the calculator here. So let me just turn this on. And you go second to the matrix menu, over to edit, say matrix A. This is a 2 by 3 matrix. I enter the sizes. And then I enter these these elements, these entries. There's 1, 2, 3 for the first row, and 3, -5, -2 for the second row, and then I'll get out of here, right? Quit. Go back to the matrix menu, over to math, and scroll until I see RREF. Again, don't confuse this with REF. That's row echelon form, or just plain echelon form. RREF is reduced row echelon form. I go there, and then what matrix do I want to put in this form? Go back, put under names matrix A that I have there, the 2 by 3, and here we have it. All right. So putting this into reduced row echelon form gives me the following row equivalent matrix. Now again, I could call this A prime, right? Just so I know it came from A. It is an echelon form of A. So 1, 0 for the first column, 0, 1 for the second column, 1, 1 for the third column. All right. And then look for your pivots. All right. The pivots are those those leading non-zero entries with zeros below and above them in reduced echelon form. So in this particular matrix here, in this echelon form, this 1 is a pivot, right? It's the first non-zero entry in this row with zeros below and above it. And then the first non-zero entry in this row with zeros below and above it, this one. And then, so I'm noticing that there are 2 pivot columns, right? 2 columns with one of these pivots in it. And there's 1 column that does not contain one of these pivots, right? So there's 1 non-pivot column. And there we go. Rank nullity. Alright, so looking at that matrix in echelon form, reduced echelon form, we are seeing that the rank of the matrix, right, the rank of A is equal to 2. Again, so again, down here, the rank of the matrix A then would be 2. And the number of non-pivot columns is going to be the dimension of the null space. That's the nullity of our standard matrix A is 1. And as I mentioned earlier, the rank of the standard matrix is the same as the rank of the transformation. So the rank of the transformation is 2, all right, which, by the way, is the same as the dimension of the codomain. Right? That is equal to the dimension of R2, the codomain. That tells me that the range must be equal to R2. Everything in R2 is going to be an output. So by a statement I made earlier, right, since the rank of the transformation is equal to the dimension of the codomain, T must be onto. Okay, so we know that T is onto. Every vector in R2 is mapped to by some vector in R3. And we saw earlier too that the nullity, right, the nullity of the standard matrix is the same as the nullity of the transformation, right? So the nullity of T is 1, which is not 0, right? 1 is clearly not 0. So that means the null space, right, of this has a dimension of 1, all right, meaning there are going to be infinitely many vectors in R3 that are all scalar multiples of 1 vector, right, the dimension is 1, that will map to the 0 vector. So that tells me that the null space is not just containing the 0 vector. So we can tell right away from that then, since the nullity of the transformation is not 0, T is not 1-to-1. Right. Therefore, this particular transformation is not invertible. Right? In order for a transformation to be invertible, it has to be both 1-to-1 and onto. This is not both. So now we can also say that T is not invertible because it's not 1-to-1. It's got to be both 1-to-1 and onto. We can also say that T is not an isomorphism. Right? Remember, an isomorphism, going back a ways, and not that long, but an isomorphism was a linear transformation that was invertible. Right, so we could also say that T is not an isomorphism, and we can say that R3, well, since they have different dimensions, R3 and R2, you know that they're not isomorphic, but just because one transformation isn't an isomorphism doesn't mean that the domain and codomain aren't isomorphic. They may be, so I'm not going to write that. All right, but again, we can say a lot just from those things. And then look, that Rank-Nullity Theorem coming into play, right? The rank of the transformation plus the nullity of the transformation is equal to the dimension of the domain. Right, that's what I said earlier for the rank nullity. The domain here is R3. 2 plus 1 is indeed equal to 3. And that's the same as the Rank-Nullity Theorem for a matrix. The rank plus the nullity should be equal to the number of columns, right? You see the number of columns of the standard matrix was 3. The rank plus the nullity is the same number, 2 plus 1 equals 3. So lots of stuff we can say just by simply finding a standard matrix that represents the transformation and putting it into an echelon form, counting pivot columns and non-pivot columns. You can say a lot. All right. So I have one final. Now that was a transformation between some Euclidean spaces. I have one final example where again I'm asked to simply find the rank and nullity, and then we can just say a few things about the transformation once we know the rank and nullity. Here I have a transformation linear, right? I'm told it's linear, and again you can verify that it's linear. Check the additivity and homogeneity properties. I have a transformation from P2 to P4. Now remember, P2 was the set of all polynomials of degree 2 or less. P4 was the set of all polynomials of degree 4 or less. And here's the rule, right? I take a polynomial of degree 2 or less, my input, and the output is I just multiply that by x squared. Right, if you take a polynomial of degree 2 or less and multiply it by x squared, you're going to get a polynomial of degree 4 or less for certain. All right. So in this case, right, if I want to find that standard matrix, right, these are non-Euclidean spaces. Right, these are non-Euclidean. Right, so, sorry, that's kind of faint there, blurry. Non-Euclidean. So that means I have to use coordinates if I'm going to try to find this standard matrix for the transformation. And if we're doing coordinates, we're going to be talking about coordinates relative to the standard bases for the domain and the range, or sorry, the codomain. So I'm going to call E1, a little fancy E1. This will be the standard basis for the domain. For P2. Remember, every polynomial of degree 2 or less is some multiple of x squared plus some multiple of x plus some multiple of 1, right? So x squared, x, and 1, these three vectors, right, these are three polynomials of degree 2 or less, form the building blocks. These are the simplest building blocks for all the vectors in P2, right? I can make any polynomial of degree 2 or less by taking a linear combination of these three. And similarly, I'll say E2, let's have that be the standard basis for the codomain, right, for P4. And very similar, right, for P2. Every polynomial of degree 4 is some scalar multiple of x to the fourth plus some scalar multiple of x cubed plus some scalar multiple of x squared plus some multiple of x plus some multiple of 1. All right. So again, these 5 polynomials here, x to the fourth, x to the third, x squared, x, and 1, form the building blocks, the simplest building blocks for all the polynomials of P4, right? I can write any polynomial of P4 as a linear combination of these 5, and these 5 are linearly independent. All right, so we're seeing that the dimension of P2 is 3, and I'll write that up here. Right, we're seeing that the dimension of the domain is 3, right? Because I found a basis for it that has 3 vectors, 3 polynomials. And the dimension of the codomain, right, P4, is 5. Right? A basis with 5 vectors in it. All right. Now keep the order that these are in mind, because when you write coordinate vectors, order matters, right? The order that the standard basis vector, the basis vectors come in matter for, because they correspond to the order that the coordinates come in. All right, so here, so P of x, my input, right? I'm going to translate my input into coordinates. Now P of x, right, is a polynomial of degree 2 or less. So every polynomial of degree 2 or less looks like this. Some number a times x squared plus, and let's assume these are real numbers, so real number a times x squared plus some number b times x plus some number c. All right, so if I translate this into the coordinates, right, what's the coordinate vector of P of x with respect to basis E1 here, right? The standard basis for the domain. And it's going to be a vector, a column vector, coordinate vector. And the first component, right, will be the coefficient of the first standard basis vector. Well, the coefficient of x squared in this is a. Then the second component will be the coefficient of the second basis vector, which is b. Third component will be the coefficient of the third basis vector, which will be c. All right. So I'm going to change my P of x into its, into its corresponding coordinate vector in a minute. And then the output, do the same thing. The output is, x squared times P of x, which if I multiplied this polynomial by x squared, it would just simply be a times x to the fourth plus b times x to the third plus c times x squared. All right, but now I'm going to convert this to its coordinates. Right, what's the coordinate vector for x squared times P of x? The coordinate vector for the output. Now the output, though, is from P4. Right? The outputs are going to be from the codomain. So we're going to write the coordinates with respect to the basis E2, right? The standard basis for the codomain. Now the codomain had a dimension of 5, so I'm going to have a 5-component vector here. And again, down the column, each component is just the coefficient of the vector from the standard basis in the order that they came in that I wrote. I wrote them in this order. So the first component will be the coefficient of x to the fourth in this output, which is a. Then the coefficient of x cubed, which is b for the second component. Coefficient of x squared, which is c. Coefficient of x is 0. Coefficient of 1 is also 0. There's no constant term. So here's the output written as a coordinate vector. All right, so then we can take our transformation up here, this rule, and translate it, and I'm going to take this to the next page, and write it using coordinate vectors instead. Or what they might call the coordinate vector representation of this transformation. All right, so on the next page, I'll just go up here, write it lightly. So we'll see we have T of, and then again, instead of my input vector being P of x, I'm going to translate that, use the coordinate vector for P of x, right? This A, B, C, and let's not forget that these are coordinates relative to basis E1. Okay, I'm just writing a little E1 subscript just to remind me, right? Because this vector with 3 components, this is not a vector from P2. It represents a vector from P2. Right? These are the coordinates of a vector from P2. Equals, and then my output, the x squared times P of x. Again, I'm going to write the coordinate vector here for the output, which was this A, B, C, 0, 0. And just to remind myself, this is not an output vector. This is not an output. This is not a vector from P4, right? This is not a polynomial. It represents a polynomial. They are the coordinates with respect to basis E2. So I'm going to write that as a subscript to remind me that this is not the output. This is representing the output. Right? These are the coefficients of the output, the coefficients of the standard basis vectors from E2 here. All right. So now what we've done, all right, what you do when you do this, right, change a transformation to its coordinate vector representation, is I've taken a transformation from P2 to P4, and I've written it as a transformation that's like a transformation from R3 to R5. Right? I said it's like it, though. It's not exactly. Remember, these are not from R3 and R5. They actually represent. Right? They look like they're from R3 and R5, but with these little subscript of the bases here, they represent vectors from P2 and P4, even though they don't. They aren't exactly vectors from P2 and P4. All right. So again, linear transformation. I'm told this, so I should be able to express the output as a matrix, which will be a 5 by 3 matrix, right? The dimension of the codomain by the dimension of the domain. It's going to be a 5 by 3 matrix, 5 row, 3 columns. I can represent the output as this 5 by 3 matrix multiplied by my input coordinate vector. So down the first column, the coefficients of the first input variable a, 1, and then a bunch of zeros, right? There's no a's the rest of the way. It's again 5 rows, so 5 there, right? 1 and 4 zeros. Then down the second column, the coefficients of b. Well, there's no b in the first component, 1 b in the second, and then no b's in the rest of them. And then the coefficients of c. No c, no c, 1 c, and then no c and no c. There's the standard matrix, this 5 by 3. Multiplied by the input vector, right, the a, b, c, and again, just to remind myself that this is not the actual input, it represents an input. I'm going to put a little subscript. These are coordinates with respect to basis E1 for the domain P2. All right. Now so here's the standard matrix. Again, I'll call it A. The standard matrix for this transformation. And if you look at it, it is already in reduced echelon form, right? The first non-zero entry, first of all, any rows full of zeros are at the bottom. And in each row, the first non-zero entry is a 1 with zeros above and below it. The second row, first non-zero entry is a 1 with zeros above and below it. Third, first non-zero entry is a 1 with zeros above and below it. This is already in reduced row echelon form. Right. So now I just look at the pivots, right? Those leading ones in each row. So there's a pivot there, pivot here, pivot here. So the number of pivot columns in this echelon form, well, again, the matrix itself is already in echelon form, so the number of pivot columns is 3. And the number of non-pivot columns is 0, right? Because every column of this standard matrix has a pivot in it. So, remember the number of pivot columns, that was the rank of our matrix. So the rank of the matrix is 3. And the number of non-pivot columns in an echelon form of our standard matrix, which this is, that was the nullity. Right, the nullity of our matrix is 0. And then I go back and now I can say all sorts of stuff about transformation T. Right. So this transformation up here, right, that I started with from P2 to P4 has a rank. The rank of this transformation, again, is just the rank of the standard matrix, 3. Right. Now look, the rank is 3. this is not equal to the dimension of the codomain. Right? This was 5. Remember I said dimension, it was dimension 5, right? Remember, the rank of the transformation is the dimension of the range. All right, so the dimension of the range has dimension 3, but the codomain has dimension 5. That means there have to be some vectors, there have to be some polynomials in P4 that aren't going to be mapped to. All right, so this tells me that T is not onto. Right, T is not onto. There are going to be polynomials of degree 4 or less in the codomain that would not be mapped to by this particular transformation. All right. And you can find an example, and if you like it, it'd be pretty easy. Basically, any polynomial that has a constant term won't be mapped to. Right. We're also seeing the nullity of A, right? The nullity of our standard matrix, that's the same number as the nullity of the transformation. So the nullity of the standard matrix was 0. The nullity of the transformation is 0. Meaning that the null space of this transformation is only containing the 0 vector. The only polynomial that'll map to the 0 polynomial is the 0 polynomial. Right? The 0 polynomial here will map to the 0 polynomial there, and that's the only one, according to what this is saying. And remember, when the nullity of a linear transformation, which this is linear, when the nullity is 0 or the null space contains only the 0 vector, that linear transformation will be 1 to 1. So T is 1 to 1 this time. Meaning, if you were to take two different polynomials from P2, they would map to two different polynomials in P4 all the time. Right? You're not going to have two different polynomials in P2 map to the same polynomial in P4. That will not happen. This is a 1-to-1 transformation. Additionally, notice that T is not onto, so T is not invertible. Right? It's got to be both. A transformation has to be both 1-to-1 and onto in order to be invertible. So again here, T is not invertible. Right. In fact, the only transformations where you could possibly see an invertible transformation are ones where the dimension of the domain and the dimension of the codomain are the same. Right here, they're different, and in the last example, they were different as well. Right away, all right, if the dimensions of the domain and the dimensions of the codomain aren't equal, the transformation is not going to be invertible. All right. Or the inverse won't be a function. I mean, every transformation has an inverse. It's just the inverse will not be a function or satisfy a legit definition of a transformation. And I've discussed that in other videos, in another video as well. But okay, I mean, this is it. Oh yeah, and look, the rank plus nullity, right? I forgot about the rank plus nullity. Right? If you take the rank of the transformation, add the nullity of the transformation, you're going to get the dimension of the domain. And the domain was that P2. And this is 3 plus 0 equals, and we saw earlier the dimension of P2 is 3. 3 plus 0 equals 3. Checks out. All right, same thing for the standard matrix. Right? The rank plus the nullity of the standard matrix should equal the number of columns. And we're seeing that here. 3 plus 0 is 3, and there are 3 columns in the standard matrix for this particular transformation. Wonderful. Alright, so hopefully finding the rank and nullity aren't going to be such a chore. You simply have to find the standard matrix associated with that, with the given linear transformation. Then through either row operations or use of a calculator, put that matrix into an echelon form, whether it be row echelon form or reduced row echelon form is fine. Count the number of pivot columns in that echelon form, count the number of non-pivot columns in the echelon form, and you'll have your rank and nullity of the transformation respectively. And the rank plus the nullity of a transformation should always, of a linear transformation, should always add up to the dimension of the domain. You might want to check all that. Also, once you know rank and nullity, you can very easily state if the transformation is, one-to-one or onto or both. Great. All right, so hope you enjoy practicing problems of this nature, and thank you very much for watching.